So first, real quick, I just want to acknowledge our partners and especially the California Department of Water Resources who funded this project. So I'm going to talk about IR-QIV, the technique that Todd introduced. But since what drove development of this is an application that's a little bit different from sort of the classic discharge monitoring that we've been talking about a lot of this workshop, so I'll motivate our application, and then I'll go through the details of how we do our measurements and share some results. So we're motivated by a fishery management problem. So this is our field sites are in California. This is California on the West Coast. That's the San Francisco Bay. And we work in the Sacramento-San Joaquin River Delta. Which is a system with, there's lots of channels, there's lots of natural and human-made channels. The whole system is tidally forced. There's all sorts of flow diversions, pumping, things like that. So it's a very complex hydrodynamic system. And specifically, the issue has to do with migrating fish. So juvenile fish hatch up in the headwaters of the river. They need to navigate through this system out to the San Francisco Bay and to the ocean as part of their life cycle. But depending on the navigational choices that they make, they can either sort of choose a short route and make it out there, or they can end up meandering through the system, which means a longer transit time exposes them to predation, lowers survival rates. So in order to increase survival rates of some of these species, what the state is doing is they've identified sort of key points where making a wrong turn, if you will, can lead to more significant impacts. And at those sites, they're trying to guide the fish towards the correct navigational choice. So they're installing these fish guidance structures. And the idea is that they don't reach all the way down to the bottom of the river. They're not diverting the flow. But the idea is to create hydrodynamic conditions that fish can sense and respond to, and that will cause them to end up traveling down the branch of the river that's better for them than the other. And the way that these studies are done is the biologists will release a large amount of fish. They'll take thousands of juvenile fish, implant them with transponders, and then over a course of several days or even several weeks, release them kind of on an ongoing rate and track their progress through the system, and especially at sort of key points along their path. So they want to see how those fish interact with the hydrodynamics. This is going to happen over a long period of time, and they need to know at any time of day what the hydrodynamics are. So we were asked to develop a system that would be able to measure over a large area continuously, 24 hours a day, for an extended period of time, so for days or weeks even at a time, and be able to measure instantaneous velocities and length scales down to the size that fish respond to, so the size of the fish themselves. So that's our motivation for all of this. The basic idea is very simple, should be familiar to anyone who's done large-scale surface measurements. We have our camera up here, and this is an example of an infrared image that we'll get back to in a second. And continue with methods. So a bit of an aside, all of our analysis is implemented in our own code, written in the Julia programming language. Julia is a relatively new open source high performance language that's just very easy to work with. And the main key to our method is this camera. So this is it's a 1 megapixel resolution camera. It has a cooled INSB sensor. And the key is the sensitivity. So it's thermal sensitivity is better than 25 millikelvins. But the trade-off is that it's large, it's heavy, it's power hungry. The sensor in here needs to be cooled down to around 70 Kelvin to operate. So it needs a lot of power and size to do that. But it captures these beautiful images at the surface. So this is, Todd showed a version of this that was rectified. This is the raw images. You can see all this detailed texture at the surface. These are those boils that Todd was talking about that are an expression of turbulence that was generated at the bottom. The way that we're looking at the image now, since it's not rectified, the length scales might seem larger, closer to the river, but this is just perspective distortion. Okay, a few words about image quality and image acquisition. This is a sequence of images at that same site, spanning sort of from late evening through the night. And you can see that at different times, the image quality is different. The pixel dynamic range is much better, sort of, in this case, towards the dawn hours. So when we have images that have this type of quality, then everything's great. We can get very good velocity results without needing to do any kind of pre-processing or anything like that, just working on the raw images. But even when we're sort of in this, this regime here, we might need to do a little bit of contrast enhancement or a little bit of filtering, but we can still get very good velocity results. And what is driving those changes in image quality is essentially air-water temperature difference. So the patterns that we're actually sensing here, I hadn't mentioned, but we're talking about temperature gradients across our field of view at the surface of the water on the order of 0.1 degrees or even less than that, which is why we need that sensitive camera. But this is in orange, sort of a visualization of the pixel dynamic range over time. And in black, this is the difference between the bulk water temperature and the wet bulb air temperature. So that the air temperature, once you account for relative humidity. What we found at this site with this camera, this is something that would vary a little bit from depending on your measurement. When we have a difference of greater than 3 degrees centigrade between air and water temperature, then we get those very high quality images. When it's less than that, then the image quality becomes graded a little bit. Our pattern tracking method. So as Todd mentioned, we use MQD. We found that it performs better when we're looking at images that have a range of intensities or more of a continuous range as opposed to a collection of sharp, bright, or dark particles. The penalty you pay here is a little bit slower performance than cross-correlation methods, but this MQD can also be accelerated using FFT algorithms. And once you do that, you're a little bit slower than cross-correlation, but you're in the same ballpark. We do our image tracking on raw images, that is with perspective distortion. This makes sense because the region over which we're performing that analysis is not that large, and perspective distortion is not going to be very significant over a region of just a few pixels for each search region. It also means that we're not doing any kind of interpolation on the images that we're using for searching. And it turns out that it's more performance friendly. The method that we use for georeferencing, we follow Holland et al. So we have basically 3 stages. We do an intrinsic calibration, which is to characterize the camera and the optical setup. In our case, we're really only looking at radial distortion in the lens system, which is very important to correct for. Excuse me. The next step is an extrinsic calibration. That would be in the field. So we use GCPs. Lots of different people have talked about that in the workshop. And then finally, after we've calculated our surface displacements in pixel space, we georeference those to get to velocities. So we use our water surface elevation that we measure separately, excuse me, and project the pixel coordinates onto the level of the water surface and translate into physical displacements. But of course, as has been mentioned a lot today and yesterday, your measurements are only going to be as good as your georeferencing. So to explore what kind of uncertainty we're facing, we took a pretty simple approach. We run Monte Carlo simulations. So our inputs to this georeferencing method is the water surface elevation and the pixel and physical coordinates of our GCPs. What we do is we take our best estimate of what those values are, calculate a transformation from pixel coordinates to physical coordinates, and then we start perturbing randomly all of those inputs and look at what that does to the outputs and calculate statistics of how our spatial referencing will change across the field of view as a function of uncertainty in the inputs. So this is a plot of a 95th percentile of that kind of calculation. We can see that essentially as we get farther away from the camera, the uncertainty grows. This is because of simply because of the oblique viewing angle of the camera. So the farther away we are, the more uncertainty will be introduced. This kind of plot is very useful for planning and for getting a general sense. But when we're taking a single measurement, we actually have one set of unknown noise or error in our inputs. So to sort of look at the implications of that, this is a single case corresponding to sort of a 95th percentile bad case, if you will. So this is sort of a case where the inputs would have had sort of larger than normal amount of noise associated with them. And we can see in this plot, which is sort of the raw uncertainty, this would say that if I'm in this region of my field of view, then my uncertainty is maybe on the order of 20 centimeters. That says if I'm a pixel, I can only say where that is in the field with that type of accuracy. But what I'm interested more than the location is what is the velocity at that point. And what the velocity is going to feel as a function of this uncertainty is related to the gradient of these curves. And since these gradients tend to be rather small, in general, we're predicting that for a typical setup like the one that we were showing in this case, we can expect that the uncertainty in the velocity measurement as a function, or the part of the uncertainty that comes from georeferencing will be on the order of 1% or less. This is sort of a worst case scenario, and we've still got less than 1% over about 85% of the field of view, and less than 1.5% everywhere. So to some results, this is actually at the first site that Todd showed in his presentation, looking down from a bridge. So this is in the Sacramento River itself, comparison over about 20 hours to an ADCP. So these are mean velocities that are averaged over some equivalent time period for the two instruments. This is a tidally forced river, and the flow reverses depending on the tide. So we have a very long range of flows, and including flow reversal at the site, and we see that the surface measurements track very well with the ADCP. This is corrected by an alpha factor of, I think it was 0.88 in this case, but it's the same factor for this entire period of time. This little gap here is just because of some equipment issues. Instantaneous velocity comparison, Todd talked a lot about this, so I'm just putting it up there. And then finally, this is our 2D, so our rectified 2D flow field. So what we're seeing in the background in the pseudo color is the instantaneous velocity at each point. And then the vectors are U prime, if you will. So the instantaneous departure from the local mean velocity. So what the turbulence is doing. And if you just look at the colors, you can see all the sort of classic momentum exchange through this boundary layer. You can see the small scales of hydrodynamic features that are present in this flow that are being captured by this method. All right, so to summarize, we make high resolution in space and in time measurements. We can measure instantaneous velocity over large 2D surfaces. The previous example I showed was around 1,000 square meters. This method can operate continuously for very extended periods because it requires no seeding or illumination. So if you're interested in talking about this, please reach out to me. Here's my email. We've got a couple of publications kind of on their way out detailing this, the entire method, and another one sort of specifically talking about our georeferencing uncertainty tools. And yeah, that's it. Thank you very much.
Yes, thank you very much for your very nice presentation, and also especially on how to tackle the uncertainty issues for the velocity tracks. Yes, are there any questions? Please just, if there are questions, just unmute and go ahead and speak.
Oh, go on then, I'll ask one. No one else is going to. I was just typing it, but I'll ask it. I was really interested to know, the cameras are expensive. Is there any potential, or have you done any work so far on the use of kind of thermal seeding or ways of, enabling cheaper cameras to be used?
Right.
And I think the pictures you're getting are astonishing, and I love them. But actually, just to be able to determine the velocity without seeing all the structure of the flow would actually be adequate for most hydrometric applications.
Right. Well, so the first answer, or the answer to the first part of the question is sort of, yes, you can seed the flow thermally. I mean, that's something we've done in the lab, for instance. I mean, basically you toss on ice cubes or boil some water and toss it over your flume. On a field scale, that might not be the most practical, but if you choose your site, then there's places where you can do this. Especially if you look at confluences of rivers, I think, and you might have actually showed an example similar to that. Mm-hmm. There was someone I was chatting with at EGU who were making measurements at the outfall of I think it was a brewery. So there was an effluent that was at a warm temperature, or we've seen examples here of discharges from downstream of power plants, or sometimes even just a reservoir that'll have a cool mass of water. So if you choose the right site, you can probably get mean velocities with cheaper cameras. There's some other sort of subtleties to the camera, though. It's not only the sensitivity. There's also this type of camera. It's built around a very different type of sensor than the sort of off-the-shelf, cheaper and lighter cameras. And it also, aside from being more sensitive to temperature changes, it's much better at freezing motion. So it's a little bit more of sort of the global shutter versus a rolling shutter type effect, or having better control over your integration time. So that type of thing also, you'd have great advantages with these cameras. But there's certainly places where you'd be able to get a subset of these measurements with a cheaper camera.